Section 2.8 is the mean value theorem. To start with, we're actually going to talk about a specific version of the mean value theorem called Rawlss Theorem. Rawlss Theorem says, suppose that f is continuous on an interval, and it's differentiable on that same interval, and f of a equals f of b. I'll draw you a picture in a sec. Then this theorem says that there is a number between a and b where the derivative is 0. So we're going to talk about what this looks like visually, and from a visual perspective, we're going to argue that this makes sense. First of all, continuous means that when I draw the image, I can't pick up my pen, right? At least in terms of a visual picture, that's what that means. The fact that A and B are written in these interval notations means they're different points. So we'll put A here and we'll put B here. And this piece of information tells you that f of A equals f of B, which means no matter what that y value is, they match. So here's f of A, f of B. They're the same thing. They're the same location on the y-axis. So they're telling you that the end points here match. Whatever height that we're at A, we're at the same height at B. So think with me. If I were to connect the point A to the point B, there's lots of ways I could do it. But no matter how I draw this, there is going to be some place where I get a slope, a derivative, a horizontal tangent line, right? A slope of 0. So imagine the worst or the simplest one would be something like this. Oops, that's supposed to be connected. Pretend. You could draw a flat O straight line too. Draw a straight line and the derivative is 0 everywhere. Agreed? Okay. So this would be the minimum description of what's happening here. I have something that looks a little bit like a parabola. Okay? And at some point between A and B, sure enough, you see this location, roughly speaking, right here, where I have a horizontal tangent line. I have a line where the slope is 0, and that location is we call C. At this location, the derivative of my function is 0. And this theorem is saying there has to be at least one place where this happens. It's not saying there couldn't be more. So I was going to draw you one more picture to give you some kind of a perspective. You could have a graph that looked something like the way we started this one, right? The beginning and the end points are the same. But between these, it does lots of moving around. So there's several locations maybe that has derivatives of 0. So this theorem doesn't tell you how many, it just tells you at least one. At least one place between A and B, there's going to be a slope of 0. Okay, so far so good? Visually, make sense? There's no way to connect A and B and not have a slope of 0 somewhere between. All right, the generalization of this is the actual mean value theorem. So jot this one down. The mean value theorem again says that you have to have a function that's continuous and it's differentiable. And there exists this point C between A and B, just like on the last one, but this doesn't say f prime of C equals 0. It says f prime of C equals f of B minus f of A over B minus A. Do you know what f of B minus f of A over B minus A is? Yeah, this is just the equation of slope. y1 minus y2 over x1 minus x2. You're looking at a slope here. So let's take a look at a graph that's doing this so that we can identify what pieces are happening here. Now, do you notice the condition that's not in this description? What's missing from this theorem that was in the previous one? Yeah, f of A and f of B do not have the description that they have to be the same. If they were the same, like they were over here, and I were to look at the line segment joining them, and I were to draw it well, its slope would be 0, right? So this theorem is actually just an extension of the one we did before. Because if f of a and f of b are the same, then on the numerator of this we're going to get 0, so we're going to get a slope of 0, and you're going to have this. Then you're going to have Rawlss theorem. Okay, so we're going to draw the picture in general form though, whereas here's a and here's b, and we're going to assume that they are different. Something like this. Can't draw it today. And we've got some kind of a curve going on between them. Something like this maybe. And what our question is what in the world does this theorem say? Well, this theorem says that if I were to connect these two with a line, that's a terrible line, but pretend that that would look straight. If I were to connect them with a line, this line's going to have a slope. So this slope here has two other places between A and B that will be the same slope. There are going to be two other tangent lines. Roughly speaking from my graph, they look kind of like this and this, that are going to have the same slope as the red line slope that I had before. And this isn't saying that there have to be two, it's saying that there has to be at least one that does this. There will be a location between A and B. So this could be a C1, if you will, and this one would be something like a C2. There's actually two in this case. But there is a location between A and B where the slope, again, if I'd drawn them well, would be exactly the same as the slope of that red line that I drew before. Again, from a visual perspective, do you see what this is referring to? And the condition here that they don't have to have is that the endpoints match. So we're going to do an example of this. And the first example we're going to do actually relates back to Rawlss theorem. It says, oh, it relates to both of them, sorry. Check the hypothesis of Rawlss theorem and the mean value theorem, and then find the value of C that makes the conclusion in whichever theorem you're working with. So there are different conditions. What are the conditions back in Rawlss theorem and the mean value theorem that match? What do we have to be able to say? Condition number one has to do with being what? Continuous. Is this function continuous? Yeah. How do you know? Do you remember?
There's no asymptotes or poles.
Right. We actually saw an argument for this back in chapter 1. We know that this is continuous because it's a polynomial. Back in chapter 1, when we talked about continuity, we talked about the fact that if you have a polynomial, it's automatically continuous. All polynomials are continuous. The second condition is what?
It's differentiable.
It's differentiable. And this is exactly the same thing. It's because it's a polynomial. All polynomials are differentiable. Again, it was a theorem that we had talked about back in chapter 1, or at the beginning of chapter 2.
If it's continuous,
Polynomial.
is it assumed to be differentiable?
No, it would not have to be differentiable. If you had this, it would be continuous, but it would not be differentiable at that sharp turn. Yes, so one does not infer the other. But polynomials are both. The third thing that will differentiate which of the two different theorems we're using is what condition?
Whether the y's are equal.
Yes. Whether f of the first endpoint, in this case f of negative 2, is going to be equal to f of 2. So we need to calculate f of negative 2 and what is f of 2. So what do we do to calculate that? Yeah, we just plug it into our equation. So this is negative 2 squared plus 1, which equals what? So what is negative 2 squared plus 1? 5, good. And then we're going to do the same thing with the number 2. What's 2 squared plus 1? 5. So these are equal. So which theorem are we going to be using? Right, so Rawlss theorem applies. What does Rawlss theorem say? Well, Rawlss theorem says that if all these conditions hold, and we've just shown that they do, then, so by Rawlss theorem, there exists a value C between the x values of negative 2 and 2 where f prime of c is 0. What this tells me then is I need to find f prime, and I need to set it equal to 0 so I can figure out what point this point C actually is. So what is f prime? F of x was x squared plus 1. What's f prime? 2x. We set it equal to 0, and we solve. Where does 2x equal 0? At x equal to 0. This is my C value. Now, if I'd had multiple C values, or even if I have a C value, I should check and make sure that it's really on the interval I'm talking about. Is this in the interval from -2 to 2? Yeah, it is. So, we'll say it this way. So C equals 0, and 0 is between -2 and 2. Rawlss Theorem said that it existed, and we found out that for sure it did, and we found the location where it did. We're going to draw a graph real quick. It says to show this with a graph. I'm not going to worry too much with this piece, but do you remember what the graph of this looks like? The graph of the original equation here. Parabola, shifted up one, so it looks like this. Sure enough, do you see the horizontal tangent line at 0? Do you see that at -2 and at 2 they should match? You betcha, it's a symmetric graph. So this is the graph that would support our conclusion. We'll finish this.